we shall start our discussion on hydraulic machines, and today we shall solve one problem related to axial flow pump. If we recall, in the last two lectures we have discussed about two different problems related to radial flow pump, and while solving those problems we have discussed about different concepts that we have learned from the previous classes in the context of radial flow pump operational issues and design issues. So, today we shall solve this problem. So, the problem is we have to read first and then we will try to solve. Let us first read the problem statement. An axial flow machine is used to pump water. So, now I am underlining these words, then it is given a few data. The tip diameter of the pump is 1.1 meter, half diameter is 0.8 meter, operating speed is 1200 rpm, absolute inlet angle is 60 degree, blade inlet angle is 30 degree and the blade outlet angle is 60 degree. So, these are given. What we need to calculate? We need to calculate the volume flow rate, rotor torque, absolute outlet angle and power required to drive the pump. Now, see, before we take an effort to solve this particular problem, I would like to discuss the relevance of axial flow pump from the application point of view. If you try to recall, in one of the previous classes we have discussed about the typical applications of different types of pumps, right. So, we have discussed that axial flow pumps are used in applications where we need higher flow rate against a low head. So, I am writing over here that axial flow pump are used supply So, this is meter cube per second. So, this is and this is meter. Now, this is what we have studied, and if we try to recall the application areas: irrigation, coal mines, where we need higher flow rate. So, areas of application, irrigation, coal mines, etc. Okay. So, with this brief recapitulation, let us now move to solve the problem. So, we will now try to solve the problem. Again I am telling, in line with what I have discussed in last two lectures, that before solving any problem related to pump, whether it is radial flow pump or it is an axial flow pump, our first objective should be to draw the velocity triangles. If we can draw the velocity triangles, it will help us to understand different parameters which will be eventually required to arrive at the requirement. That means, what we need to get from this particular problem. So, you know that so again today what I will try to draw, I will try to draw the schematic depiction of an axial flow pump, and then I will try to draw the velocity triangles. So, if we try to recall, it is very difficult, because again I am telling you have to visualize the physical configuration of the axial flow pump. My suggestion would be to visit any nearby plant, and you have learned something about this particular type of pump. It would be very helpful if you try to visit any plant wherein axial flow pump or pumps are in operation. So, that will help you to understand the concept that you have learned in a better way. So, this is this is pump casing, and this is pump impeller. Right. This is axis of the pump. So, say this is Z, right, and this is radial direction R. Now, what we need to do next? We need to draw the blade, at least one blade. So, if we try to draw using different colors. So, this is one blade, and if we draw another blade at the bottom like this. So, this is basically this is half plus blade. So, these two parts constitute together and to form the pump impeller. Now if I try to draw the so this is the flow direction. Okay. We have also discussed about radial equilibrium, and that is very pertinent in the context of axial flow pump operation. We have seen that for downstream and upstream, streamlines are parallel to each other, but when flow is approaching to the blade, then there is a radial shift, and we have discussed about why. We also have discussed the need of studying this particular aspect in the context of axial flow machine. So, now if we give say I mean this is, if we try to draw the blade say okay, and say this is point 1 and this is point 2, right. So, this is at the 1 and 2. So, 1 is pump inlet and 2 is pump outlet. So, I am taking a few minutes to recapitulate what we have learned before, because whatever we have learned, that will be required today to solve the example that we have already read. Now next task should be to draw the velocity triangle at the inlet and at the outlet. Nothing is said about we have solved one problem in the context of radial flow pump, and we have seen that sometime it is explicitly given whether we need to consider swirl at the inlet should be considered or not. If nothing is mentioned, we will not consider swirl at the inlet. If it is mentioned, this is well and good. So, for this particular case, again it is nothing is mentioned about whether inlet swirl we should consider or not, but again I am telling in the context of axial flow pump we should consider swirl at the inlet, and if it is mentioned that it is swirl free flow, then definitely we may ignore, fine. So, now our next objective should be to draw the velocity triangles, that is very important at this point of time. Okay. So, if we try to draw the velocity triangle, I will draw here first and then I will try to draw the enlarged view separately, essentially to have better understanding. So, this is the if I draw using different color again, say I am using this color, I am using this color. So, this is W1, this is U1 and this is C1. So, we have learned that these three velocities are three important components, like this is the absolute velocity, this is the velocity, flow velocity relative to the blade velocity, that is why it is called relative flow velocity, and this is the tangential velocity of the which is the blade velocity at the inlet and outlet. So, this is blade velocity at the inlet, and if we try to again mark the flow angle and blade angle. So, this is alpha 1 and this angle is beta 1, right. So, beta 1 is the blade angle at the inlet, alpha 1 is the absolute flow angle at the inlet. Next, if we try to draw the velocity triangle at the outlet, so let us now draw using another color. So, I am using this color. So, this is U2, this is C2, W2. So, this is C2. Okay. This angle is alpha 2 and this angle is beta 2, right. So, this is very important. So, we have drawn the velocity triangles. Now, it would be nice if we try to draw the velocity triangles again. So, that will help us to understand the problem in a better way. So, inlet velocity triangle, so this is absolute velocity. We have seen this angle is absolute flow angle at the inlet. So, this is alpha 1, this is inlet blade angle, this is beta 1, that is what we have discussed many times, even when we have solved problems related to radial flow pumps. So, this is U1 this component again we know. So, this is basically component of absolute velocity in the tangential direction, and that is the swirl component at the inlet. So, this component is the component of absolute velocity in the tangential direction. So, swirl component at the inlet. Similarly, this is W1 relative velocity at the inlet, and this component is W theta 1, that is component of absolute velocity, a component of relative velocity in the tangential direction, and this is basically Cz1. So, this is flow velocity at the inlet. Now, you may recall that the flow velocity which is represented by shear 1 and shear 2 at the inlet and outlet for the radial flow pump. Here we will be representing the flow velocity by Cz1, Cz. So, Cz1 it represents the flow velocity at the inlet, and similarly Cz will represent the flow velocity at the outlet. Why? See, now fluid flow takes place in the z direction. Now, if you try to recall in the for the radial flow pump, the flow takes place in the radial direction inside the pump, right, and that is why Cr1, that is the suffix r is coming to denote the flow velocity components. Similarly, here the flow takes place in the radial axial direction, z direction, that is the axial direction, and that is why the name axial flow pump is coming. So, flow is in the axial direction and z is used to denote the axial coordinate, and that is why Cz1 or Cz2 will be used to denote the axial flow velocity component at the inlet and outlet respectively. Fine. So, now if we try to relate what we have learned, what we have from the information we have from the problem statement. See, it is given that the absolute inlet angle is 60 degree and blade inlet angle is 30 degree. So, can't we write? So, basically if we try to go here, then we can write basically alpha 1 equal to 60 degree, beta 1 equal to 30 degree, right. So, this is the inlet velocity triangle. Next, if we try to draw the outlet velocity triangle, say if I try to draw over here, so this is C2, this is W2, and this component will be Cz2, right. So, this is Cz2 we have discussed just now. So, this is the flow velocity at the outlet, and this angle is alpha 2, that is absolute flow angle at the outlet, and this is blade angle at the outlet beta 2, right, and this is definitely u2, that is the tangential component velocity at the outlet. So, pump is rotating in this direction, right. Now, this is again component of absolute velocity in the tangential direction, and this is component of relative velocity at the tangential direction at the outlet. So, C theta 2 and W theta 2. Again, if we go to the problem statement and try to understand if we have any information related to the outlet velocity triangle, it is given that blade outlet angle is 60 degree. So, now it is given beta 2 equal to 60 degree. Okay. So, maybe we need to calculate alpha 2 from the problem statement. Okay. So, next I will move to solve the problem. Okay. Now, you can see operating speed is given 1200 rpm. Not only that, the tip diameter of the pump is 1.1 meter and half diameter of the impeller, tip diameter of the to be precise impeller should be, and half diameter is 0.8 meter. Okay. So, now if I try to go to the pump schematic depiction, we have to draw the schematic again. So, now it is very important, I would like to say first draw the pump, okay. So, this is known as half diameter DH and tip to tip blade tip to tip distance is known as tip diameter. So, DH and DT. In fact, we have discussed this part again I can tell you when we have discussed about the axial flow pump, I mean different issues of the axial flow pump. So, now this is, so basically this is half diameter and distance between blade tips is known as tip diameter. So, this is the rotation and as I said this is radial direction and this is the axial direction. Okay. And it is given half diameter of the pump is half diameter is 0.8. So, this is 0.8 meter and tip diameter is 1.1 meter. This is quite obvious, definitely tip diameter will be higher than the half diameter from the geometry. Now, if you try to recall, I had discussed one important issue. What is that? Whenever we will be trying to calculate flow parameters related to axial flow pump, it is very difficult to consider whether, I mean it is very difficult to say whether all flow parameters will be calculated based on the half diameter or tip diameter, right. So, basically what is done, all flow parameters are calculated based on the mean diameter. So, you may have a confusion that should we calculate all flow parameters based on the half diameter or should we calculate all flow parameters based on the tip diameter. So, it is not, we need to calculate all the flow parameters based on the mean diameter and that is dm, that is dH plus dt by 2. So, for this particular case dH plus dt by 2 would be equal to 0.95 meter, right. So, next, so one important aspect we have understood by this time that before going to solve other parameters based for this particular, not only for this problem, for all problems related to axial flow pump, first we need to calculate the mean diameter of the pump impeller. So, basically in fact I would say this is the mean diameter, right. Tip diameter is given 1.1 meter, half diameter is given 0.8 meter. So, this is the mean diameter of the pump. Next, which is most important, I mean in the context of axial flow pump we have seen, see I mean this pump or rather these pumps are used to supply liquid in situations wherein we need high flow rate against a low head. So, question is, I mean if we just try to consider two different sections, that is section 1 and section 2 at the inlet and outlet, and if we try to use the, I mean if we consider, that is very important that if we consider two sections, that is section 1 and 2. So, sections, say this is and this is section. So, section BB and section AA for this section AA and BB. Okay. So, if we consider section A and section BB, see just I am not talking about far away from the blade and far upstream and far downstream of the blade. So, basically I mean this span is not very high. So, I mean if we just look at these two sections A and BB, and if we try to apply the if we see that the flow area is remaining same, right. So, flow area, right, that is nothing but pi by 4 dt square minus dh square, right. So, this is the flow area. So, the flow area is remaining same at sections. So, basically, so this is same for sections AA and BB, right. For the constant density, or I mean if the fluid which is flowing is having constant density is not changing from section AA to section BB, right. That you have learned from fluid mechanics. For the flow, for the constant density flow, what we can write. So, for constant density flow, if we apply the mass conservation equation that we have learned from fluid mechanics, I am not getting into that, but still which is required to solve this particular problem. So, basically you can see, so Q at section A will be equal to Q at section BB, right. So, we have learned it, that is the very generic form of the mass conservation. Now, if the density is constant, then we can write area of section, I mean if we erase it, say area of section A into the flow velocity Cz1 or Cza will be equal to area at section BB into Czbb. So, pertaining to this geometry for a constant density flow, since area at section A equal to area at section BB, we can write Cz A is equal to Cz BB. So, this is what is needed to solve this particular problem, and that is why I have taken this effort here to just recapitulate. Though we have learned it, but still we have recapitulated today only because it will be required to solve the present problem. So, I mean incompressible flow special case is density constant. So, basically density constant is a special class of incompressible flow. So, constant density flow, if we write, eventually we are getting that the axial velocity, rather the flow velocity at the inlet is equal to flow velocity at the outlet. So, which is important, I can say message for this analysis, that the flow velocity is remaining same as the liquid passing through the impeller of an axial flow machine. Okay. So, now for this particular case, now what will be doing next, as you have already discussed that all the flow parameters will be calculated based on the mean diameter. So, next task will be to calculate u. So, tangential velocity u1 equal to u2 equal to u. So, right. So, u1 equal to u2 equal to u, right, since basically now you considered we are focusing at these two sections. So, these two sections wherein r is same and we are considering that is nothing but mean of the half and tip diameter, right. So, all the this is not wrong, this is what is followed to solve the problems related to axial flow pump. So, basically you can see these two sections wherein we are focusing our attention are say this is r m distance away from the axis of the pump, and already you have calculated dm. So, now u1 and u2, so those are the tangential component of velocity at the inlet and outlet will be and that is equal to u. So, since r1 equal to r2, now r1 equal to r2 equal to rm. So, this will be equal to em. So, that is pi dm n by 60. Okay. So, if you calculate, so this is pi dm we have calculated, that is nothing but 0.95 meter. It is given 1200 rpm divided by 60 and it will be coming 59.7 meter per second. So, again I am telling unit is very important. If you forget to write unit, if you do not write unit, you may not get full credit. So, this is velocity. Now, next part is very simple, just we need to look at the velocity triangles and just applying trigonometric relationship we can calculate the next task. So, you can see basically what is u. So, this is u1 is equal to c theta 1 plus w theta 1, right. So, if we write that step 1, so u1 equal to c theta 1 plus w theta 1 equal to 59.7, right. Now, what is w theta 1? So, if we try to go back to the slide, so this is w theta 1 is nothing but c w theta 1 by c z 1 is equal to what, cot beta 1. So, I can write here w theta 1 by c z 1 equal to cot beta 1 from velocity triangle at the inlet So, w theta 1 will be equal to c z 1 cot beta 1, beta 1 is given, what is beta 1? Beta 1 is given 30 degree, right. So, I am writing cot 30, right. Next, what about c theta 1? C theta 1 by c z 1. So, this is c z 1, this is also c z 1, c theta 1 by c z 1, again this is cot alpha 1, right. So, if we write c theta 1 by c z 1 equal to cot alpha 1, okay. So, we can calculate c theta 1 equal to c z 1 cot 60, right. Okay. So, now what is c z 1, right. So, c z 1 we can now plug in the value of c theta 1 and w theta 1 over here. So, we can calculate c z 1 cot 60 plus c z 1 cot 30 equal to 59.7 and c z 1 if we calculate will be equal to 25.9 meter per second, right. The moment when we have c z 1, we can say c z 2 will be equal to c z 1 equal to 25.9 meter per second, right. So, we got it, right, and that is what we have done this exercise again, that flow velocity component is remaining same. Okay. Next objective should be very important, that. So, if we now go to the volume flow rate, right. So, first let us now focus on this particular part. So, volume flow rate, or before going to look at this volume flow rate, rotor torque, absolute outlet angle and power required. So, basically we need to calculate absolute outlet angle, that is very important. So, absolute outlet angle means we need to calculate what? We need to calculate the absolute outlet angle here alpha 2. So, we need to calculate alpha 2, right. So, basically okay. So, if we write over here absolute outlet angle alpha 2, that is what we need to calculate, right, because we have already listed down alpha 1 is equal to 60 degree, alpha 1 equal to 60 degree, that is the absolute inlet angle, and we have to calculate absolute outlet angle. So, now how can we calculate alpha 2? So, can we now look at the velocity triangle at the outlet? So, now if we look at the velocity triangle at the outlet, we need to calculate alpha 2. See, we know Cz2, we also know u2. So, we have to calculate the alpha 2. So, alpha 2 is nothing but, I mean, from the velocity triangle at the outlet, what we can do, alpha 2 equal to tan inverse, right, tan inverse what? So, I mean Cz2 by C theta 2, Cz2 by C theta 2. So, Cz2 we know from this, we have to calculate C theta 2, right, which is very important. How can we calculate C theta 2, right? So, this is nothing but tan inverse Cz2 by u2 minus w theta 2, right. See if we now again look at the outlet velocity triangle, we know beta 2, we know u2. So, if we know w theta 2, we can easily calculate c theta 2, and that is what I have done, right. I have replaced c theta 2 by this term u2 minus w theta 2. Now, u2 is known. So, this is u1 equal to u2. So, if we try to recall here, u2 equal to 59.7, right, Cz2 equal to 29.5 meter per second. So, in this expression only unknown is w theta 2. If we can calculate w theta 2, we can easily calculate alpha 2. So, what about w theta 2? If we go to the next slide. So, w theta 2 from outlet velocity triangle. Okay. So, w theta 2 will be equal to w theta 2 by Cz2 equal to cot beta 2. Kindly, if we look at the velocity triangle, w theta 2 by Cz2 is equal to cot beta 2. So, w theta 2 will be equal to Cz2 cos beta 2. So, w theta 2 will be equal to Cz2 cot beta 2, and Cz2 is 25.9 and beta 2 is given, beta 2 is already given if we go to the previous slide 60 degree, right. So, that is nothing but cot 60. So, basically I mean from the previous slide alpha 2 equal to tan inverse, right, what we can write tan inverse Cz2 by u2 minus w theta 2. So, 25.9 divided by 59.7 minus 29.5 cot 60. So, you can easily calculate what will be the value of alpha 2. Okay. So, this is also done. Next, what we need to calculate, this is very important. So, basically till now I have tried to look at the velocity triangle and from the data given to calculate all the velocity components. See, just again if we look at the velocity components, velocity triangles, we can see if we know alpha 1 beta 1, if we know alpha 2 beta 2, we can calculate, already I have calculated u 1 and u 2, and then we can calculate all the velocity components. So, basically if we now again look at the problem statement, so absolute outlet angle, that is alpha 2, that we have calculated already. So, next we have to calculate volume flow rate. So, basically if we now focus, and to calculate alpha 2, we had to look at the velocity triangles, and also we had to calculate flow parameters from the given set of data. So, now next objectives should be to calculate the volume flow rate. Cube will be equal to pi by 4 dt square minus dh square into Cz, whether it is Cz1 or Cz2, because Cz1 is equal to Cz2, and if we do this, it will be coming pi by 4 into 1.1 square minus 0.8 square into 25.9. So, it will be meter cube per second, right. So, I am not going to write. So, this will be meter cube per second. So, this is one answer, this is also one answer. So, next task is, so we have calculated volume flow rate, we have calculated absolute outlet angle. Next, two important parameters we have to calculate, that is rotor torque and the power required to drive the pump. Now, again if we go to the calculate what will be the power required. So, the torque, rotor torque T equal mass flow rate into mean diameter into c theta 2 minus c theta 1. In fact, that is what we had used to drive the Euler equation for the pump in one of the previous classes. So, now if we know the mass flow rate, so this is basically rho into cube Rm into c theta 2 minus c theta 1, right. So, basically what is c theta 2? So, this is basically c theta 2. So, this is c theta 2 is equal to u 2 minus w theta 2, and if we calculate it, you will be getting the value is 44.6 meter per second. So, you can understand what is, say, we can consider flow rate if you calculate, you will be getting, answer will be 11.6 meter cube per second, and rho cube we need to go through the problem statement again. Nothing is said about the density, but if it is water, then we can consider this is right. So, we know the rho, we know the value of density, we can calculate, we know cube, that is 11.6 meter cube. So, basically if it is water, consider water, right, that is what it is mentioned, water. So, you can easily calculate, you can easily plug in the value of density over here, and that is 11.6 meter cube per second. What about Rm? 0.95 meter, and this quantity will be equal to 44.6 minus 44.6 is c theta 2, and what about c theta 1? C theta 1 is basically this. So, that is Cz 1 equal to 25.9 into cot 60, and this will come as 15 meter per second. Okay. So, we know Cz 1 already from this 25.9 and cot 60, so it will be coming as 15 meter per second. So, now if plug in the value, this is 15. So, then we can easily calculate what will be the torque. Unit should be Newton meter. So, you can plug in the value and eventually you will be getting. So, this is I am sorry. So, it will be half of 0.95 meter. So, this is half of 0.95 meter. So, unit would be very important, unit would be Newton meter. Okay. So, once we have calculated torque, then so basically again if we go to the problem statement. So, we have calculated rotor torque T, we have calculated volume flow rate Q, we have to calculate power required P. So, basically P would be then power P would be equal to T into omega. So, that is this is this will be I am writing 201 Newton meter. So, that is coming 201 into omega. So, you know the pi n by 60 and it will be coming 25.3 kilowatt. Okay. So, this is very important, right. So, you know that so once we have calculated torque into omega, that is nothing but power, and if it is we know the RPMs, from there we have calculated. Okay. So, now question is if we would like to summarize what we have discussed today. See, we had started our discussion with this problem that is related to axial flow pump. Before coming to the problem, actual problem, we had tried to discuss, rather we had tried to recapitulate several issues related to axial flow pump that we have already learned. Now, using those concepts, we have tried to draw the velocity triangles, which is very drawing velocity triangles will help a lot to solve the problem, and then we have listed down the parameter that we have from the problem statement, and then we had tried to calculate the other important components and velocity components and angle. From there we have tried to calculate what would the required parameter for this particular problem. One important aspect that we have discussed, that all the flow parameters must be calculated based on the mean diameter, and which is very important to note that for the constant density flow, since the flow area at the inlet and outlet is equal. So, the flow velocity also will be equal, that is C z 1 is equal to C z 2. And finally, we had by simply very simple, that is by applying trigonometric relationship, we have calculated rest of the parameters, and from there we have calculated the desired quantities for this problem. Okay. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.